here is the outline. We're going to provide an overview of optical test requirements and then what's driving those test requirements in terms of coherent technology trends, and then some detail about testing of coherent transmitters, receivers, and links. Then I've got a couple of application examples that we'll go into varying amounts of detail depending on how much time we have there. And then at the end, we'll do a little bit more of a deep dive on optical modulation analysis software, which I think is a big question on people's minds of, what does it do and how does it do it? And then at the end, we'll have time for questions. So just sort of setting the stage here, it's useful to kind of look at all the standards that exist, and this is far from a comprehensive list, of course, but just sort of giving a sampling of standards at varying distances from, the transcontinental type distances here at the top, which is where we see the complex optical being so important, down to the shorter reaches. Of course, in the sort of 100 meter to 40 kilometer range, I think is really where you see Ethernet dominate. But then as we continue to go to shorter links, for example, chip to module, chip to chip, once again we see the optical internetworking form involved, both here as well as at the longer distance links. And of course, on the very long distance links, we also have the ITU, like OTN type standards coming into play. So a lot of material I present today I draw heavily from the Optical Internetworking Forum, and I'll mention that as I go along, but it's a great source of information for this field. So we'll be focusing in here on the complex optical long haul area, which of course now is also pressing into metro, and Coherent is seeing application reaches all the way down to 80 kilometers. But I just wanted to point out before we shift our focus entirely to Coherent, just that even in the Ethernet world, we're seeing multi-level modulation now become important as they move to 400G. So I listed one example that we're seeing emerge from the 400 gig Ethernet working group there that involves 8 wavelengths and using a PAM4 modulation. So today we see this convergence to 100 gig across the board, as Stephen mentioned at the top, but now, of course, moving to 400 gig. So it's interesting to look at some of these modules before we dive into how we test them. So up until fairly recently, this 5x7-inch module was the MSA that was being used for long-haul transport. The 5x7-inch module contained the items shown here in the green box, although at that time the interface was not 4x28, it was a 10-lane each way running closer to 11 gigabaud. And but inside the box, then you've got any sort of digital signal processing you do on the transmit side, any soft decision FEC, and then we're going to go to the modulator. We go out onto the line, and then on the way back we have our coherent receiver. We'll have a local oscillator for our coherent receiver that down converts the signal, and then we go to our receive side signal processing chip that would do any soft FEC termination and then bring you back to the line rate that the framer is at. Now, as we move from the 5x7-inch module to some of these smaller modules now, as the OIF is doing, we don't necessarily have the same dividing line. So, for example, there's a CFP version that I'll mention in a second also that does include all of this just as the 5x7-inch module did. But now we're seeing this with the CFP2 ACO project at OIF, the dividing line moving to in between here, so that the really expensive, important ASIC that does the processing both on the transmit and the receive side can be pushed out of the module, thereby reducing its power dissipation and making things more flexible for for implementation. So there's still an argument, okay, what's better, putting the ASIC inside the module or outside the module, but there's no questioning the fact that it certainly makes this module smaller and consume less power if you push the ASIC outside of the module. So then looking at what that means in terms of, okay, so how does everything stack up here in terms of reach and faceplate density? So on the horizontal axis, which it looks like I lost the arrow on the horizontal axis, we're going from, the tens of kilometers on the left to thousands of kilometers on the right. And then the vertical axis here, what we're plotting is the speed per CFP port width. So the idea is what's the raw gigabits per second, but how much can you jam into the width of a CFP port. That's seen here. This is taken from the CFP MSA document, and the CFP module itself is 82 millimeters. So what this slide is trying to show you is, okay, well, what can we jam into that 82 millimeters? We see, with 100 gig units, some of them are very narrow. Here's a 100-meter variant. It's extremely small, the QSFP28, and because of its small size, you get a very high density of gigabits per second in the IEEE standard. And this is kind of a guess. I'm not sure exactly what's going to emerge from the IEEE 400 gig group, but potentially it seems like this variant will exist, which would do 400 gigabit per second in a much smaller form factor than CFP, approximately the size of a CFP2, and that would give us 800 gigabit per second in that CFP width. Now going over to the OIF here, we're talking about the longer distance modules. Here we have the older 5x7 inch module down here at the bottom, of course very low density because it's a big module. And then now as we move into the CFP pluggable coherent, we see here the full CFP module. I believe there was an announcement by Acacia at OFC, and I know there's other suppliers for this sort of thing where the DSP is actually included in the CFP module, but then it requires the full CFP width. To get more density, the DSP can be kicked out of the module. Now you can go to the CFP2 ACO, analog coherent optics, and that gets you the smaller width. And so if you do 100G in that smaller width, now you've got 200 gigabit per second in that CFP width. But if you do 16 QAM with that same module, now of course you're going to double the gigabits per second you can get in that faceplate. So you can see the progression here towards higher and higher faceplate density, both on the sort of the client side or the backplane side, and also on the line side, things are continuing to move up. So as we do progress, both in terms of density and data throughput, of course this puts a huge load on testing. I want to just quickly, just for fun, if you haven't seen some of these specifications, it's kind of blurry, but just give you a feeling for what's in some of these different types of standards and interoperability agreements. So a typical electrical link standard that you would expect people to be compliant to will have terrifically detailed test method. And so this is going to tell you, what type of test equipment to use, how to hook it together, what the settings should be, how to calculate the results. It really very detailed so that there's no ambiguity about how the test is to be performed. What you see over on the long haul side, and I'm sure most of our audience here is familiar with this, is we don't really typically see that level of detail. And so here's an example of an OIF interoperability agreement where the actual electro-optic properties are in an appendix, which is informative. And the idea is that we're going to let the market work this out. And it gives the transmission system providers the opportunity to work up their own secret sauce and figure out how best to provide the greatest value to the market. And then they're going to work together with their supplier base to be able to provide whatever it is that they need. So for this type of specification or interoperability agreement, what's going to be important is that we be able to customize the solution and to be able to test the specific numbers that are being called upon for different application requirements. All right, so just a couple more slides to kind of set the stage before we dig in. All right, so just a couple more slides to kind of set the stage before we dig into the detail here. I mentioned a second ago about the pluggable Coherent that is now enabling us to bring the cost down far enough to really start moving into metro applications, as well as just improving faceplate density across the board. And of course, the work on the very short links helps to enable this, because it doesn't help to get higher faceplate density on the line side if you can't bring that all the way back through to the backplane. And then another exciting thing that's happening at the OIF is there's now a greater than 40 gigahertz proposal for the transmit and receive side modules. So we can expect to start to see higher line rates being made possible by this interoperability agreement work. And then the white paper, which I'll draw from also today, is also very interesting and exciting, the types of things that are being proposed there. So all of these things create a lot of excitement and new developments in the for coherent pluggable modules, and of course then create into the detail importance we handle this on the testing side. This is a little excerpt from the OIF white paper showing FlexGrid. You know, for years we've lived with the 50 gigahertz grid, originally the 100 gigahertz ITU grid, and but that really doesn't allow you to take advantage of the spectral density that you can get when you start going to these complex modulation methods that enable you to really compress the spectrum to the bare minimum. And also being able to be flexible about your grid lets you pack in different types of signals, which is being proposed here in the white paper. One thing I wanted to point out is that the FlexGrid also makes possible the management of multiple carriers as one channel. So one WDM channel could actually have more than one carrier in that channel. And so we also need to deal with that, to be able to select out one carrier in a WDM channel and to analyze that particular carrier. All right, and this is just a little slide I lifted from a presentation at the OIF referenced down here. And the idea is just to kind of give you a feeling for, again, how it's important to look at different formats and different rates, just as we saw in our poll question where we really couldn't narrow this down at all. People want it all. And so the same system might do QPSK, 8 QAM, 16 QAM, 32 QAM. As you go to the higher QAM levels, you can reduce the baud rate, and so that's going to let you get more channels into a particular fiber. But the higher QAMs can't go quite as far, and so you might have to trade off the total data throughput of that fiber just to be able to go the longer reach. And so being able to change rates, and here the 32 QAM would be approximately 25 gigabaud, and the 8 QAM would be closer to 56, I believe, to achieve the same data throughput. So being able to adjust your rate to compensate to go longer distances is something that's really exciting and important in these emerging standards. Okay, so and then obviously in order to pull this off, there has to be a lot of signal processing both on the transmit side as well as the receive side. And we're used to thinking about all the receive side equalization and maybe doing a little bit of pre-compensation on the transmit side. Well, if you really want to pack those spectra in, if you really want to be able to switch dynamically from 16 QAM to 8 QAM or whatever it is that you need to do, there needs to be a ton of signal processing also on the transmit side to handle all of these things, the symbol mapping, dispersion compensation, and to give the pulse shape that you want. You can actually design what the spectral shape is going to be so that you can put these things next to each other. The receive side processing, of course, is something we've needed all along in the Coherent area, and I'll go over that in more detail later in the presentation. Okay, so now that we've had a chance to sort of set the stage about what is driving the need for coherent test and measurement, and we've talked a little bit about what's popular, and it seems like everything's popular, so it's a little bit hard to focus the presentation, but we'll now go in and talk about some of the details. Okay, so here is basically an overview of a coherent test system from end to end, from the data source to actually receiving the bits. So on the data source, I'll provide some different examples. It could be pulse pattern generator or a D to A converter, arbitrary waveform generator. Well, once you generate the data, now we need to translate that up to the optical carrier frequency. And for that, we use optical modulator, an IQ optical modulator that's going to move that electrical data up onto the optical frequency. And now we have our optical test signal. So if you were going to test a receiver, you could possibly now use this golden transmitter to test the performance of your receiver under different impairments. But now continuing on, if you had a transmitter or a transmission system you're trying to test, then you need the coherent receiver, which is going to downconvert that optical signal to baseband, which we can now digitize with A to D converter. And now lots of math has to be done in order to extract that, and finally get down to the ones and zeros that were transmitted by the data source. But these three blocks together can be thought of as a golden receiver that you can then use to test your transmitter or transmission system. And then for all those blocks, then I have a sort of examples from the Tektronix product line for the data source, the transmitter, the coherent receiver, and the digitization, and then of course the analysis software. So now focusing in on the pulse pattern generator. The pulse pattern generator is probably what we're all most accustomed to. Basically putting out a binary pattern, and these are available up to 32 gigabit per second and higher, very fast rise times. But one thing I want to point out is that you can use these also to make multi-level signals. You can take two pattern generators and you can attenuate one of them and then resistively combine, and that's going to give you a 4-level signal, for example. Multi-level signals made in this way tend to have very open eyes because the very fast rise times you can get from the pulse pattern generator. The thing about pulse pattern generators is typically they don't come with the ability to do precompensation. They do include other features like, for example, jitter insertion, things like that. But usually if you're going to do precompensation, you're going to need to add another box. Usually continuous time linear equalizer, CTLE, is used if you need to do precompensation before going to your transmitter. The alternative to the PPG is the arbitrary waveform generator, as we call our product, or basically D to A converter, that's going to allow you to create arbitrary waveforms. So this really now enables you to craft any optical waveform that you might want in order to compensate for cable losses or the E to O converter transfer function, etc. So that's very powerful. And here's an example doing a 256 QAM at 20 gigabaud with one of our products. And you would think actually in the literature it's recommended to have a 7-bit E-knob in order to pull off a 256 QAM constellation, and our product is actually closer to 5. But you can see that nonetheless it was able to do a pretty darn good 256 QAM constellation. And this sort of raises a point about one of the metrics you want to keep an eye on, both on the transmit side, if you're talking about arbitrary waveform generator, as well as on the digitizer side, which is E-knob. E-knob is the effective number of bits. It's basically just log base 2 of the signal to noise and distortion ratio. So it basically gives you an idea okay, the unit may have more bits than that. In our case, this is a 10-bit D to A converter, so the unit has more bits than that. But what can you expect to use practically when you take into consider the noise and the distortion? However, the E knob is usually quoted in a certain bandwidth. If you use less bandwidth than that, you're letting in less noise, you're letting in less of the harmonic distortion, and so the E knob actually gets better as you low pass filter. So I think what we're seeing here in this ability to do the 256 QAM at 20 gigabaud is that because the products in question have a lot more bandwidth than that, once you apply that low pass filter, you actually get effectively a higher number of bits. So sometimes it's the point then that when you look at, for example, digitizers, having more samples per second than you really need can turn out to be a big advantage because then you can use low pass filtering to really improve your signal to noise ratio. And then here's another example. In this case, we used both E to O conversion and O to E conversion. So this has been transmitted over fiber, and showing how you can pre-compensate for the cables and modulators, and also then achieve the spectral shape that you're looking for. In this case, it was a raised cosine type spectral shape with a roll-off factor of, I think it was 0.35. So you can get exactly the spectrum that you want. And here's the IQ modulator I was talking about before. Basically, the way it's done in lithium niobate is you have a modulator for in-phase, modulator for quadrature, and then you can affect the relative phase between those by a phase shift on the lithium niobate. So those three things need to be controlled for both polarizations. So it turns out to be somewhat tricky to control one of these dual pole IQ modulators, and so the bias control of the modulator turns out to be kind of an important part of the transmitter. So when you're talking about measurements, then being able to measure the performance of the modulator is important. How well is it biasing the modulators? How well is it biasing the phase? And these are all things that you can measure with an optical modulation analyzer. Down here is some example of the spectra that you can get out of a lithium niobate modulator. And a lot of this also applies if it's an indium phosphide. Here, if you have on the far right is what you get if you do basically on-off, fast rise time switching. You get these multiple lobe sync function that happens because of the fast rise time. It's basically the Fourier transform of a square pulse. And so the spectrum ends up being a lot wider than you might expect. This is for a 10 gigabaud signal. But if you can spectrally shape this, that is, don't use a fast rise time square pulse, instead use a raised cosine type pulse, now you can get a square shaped spectra, and so you can get a lot higher baud rate here. This is 28 gigabaud, fits into actually a narrower slot than the 10 gigabaud because of the spectral shaping. So just another example of how being able to craft arbitrary waveforms is increasingly important. Now on the receive side, this is perhaps a little more familiar, but basically what we need to do is downconvert the optical signal. So we're going to bring the signal in, and it's going to get mixed with a local oscillator. So a lot of the measurements you're going to make are going to be all relative to that local oscillator. So the quality of the local oscillator is important, how far it can tune, because what's going to happen is that the electric field from the local oscillator is going to mix with the electric field from the optical input signal, and you're going to get both the in-phase and quadrature outputs out of the mixer, because it can mix with both the in-phase and the 90-degree shifted local oscillator. And so these mixer products are all going to be signal minus local oscillator. So the phase will be phase of signal minus phase of local oscillator is what you're going to get over here at the mixer output. And then once you have the downconverted optical signal down to baseband, then it needs to be digitized and processed so that you can actually see the constellation and eye diagrams. So when you look at a coherent receiver then for test and measurement purposes, one thing is in order to handle multi-carrier signals to keep in mind is the dynamic range, the common mode rejection ratio, image rejection, all these things, weigh on how able the receiver is able to handle more than one signal. And then on the digitized side, usually an oscilloscope is used on that side. An oscilloscope can actually be really handy for test and measurement because they have very deep memory. For example, ours I think has a giga point of memory for each channel. So that lets you get about 5 milliseconds of data at 200 gigasamples per second and really gives you a good look at what was happening over a fairly long period of time. So the oscilloscope gives you that sort of deep memory advantage. And then the data can be processed offline so that you can see what's going on. So now as we dig into the optical modulation analyzer side of things then, so now for a moment we're talking about testing the transmitter or transmission system. There are a few things that are important here. Low EVM, I'll talk about what EVM is in a second. Future proofing, being able to hook the whole thing together with the minimum amount of loss, and be able to customize to measure the things that you need to measure. So first of all, EVM is a measure of how close did you get to putting the symbol where you wanted to put it. So if you're doing, say, QPSK, you've got 4 target symbol locations, and you want to try and hit those targets. And your transmitter may or may not do that. And so if you were trying to put the symbol down here where it's saying reference, but the symbol actually went way up here where it says measured, then there's an error vector that goes from where it was supposed to be to where it actually was. And the magnitude of that vector then is a magnitude of how far things went wrong. So what we can do then is for a whole group of symbols, we can RMS average the magnitudes of all those vectors and then divide by some suitable number to express it as a percent. Now, there is an IEC document that standardizes this, which is referenced here, and that's where I got the figure. And in that document, it says that you should use the largest reference symbol as the denominator. So everything's relative to the largest reference symbol. But there are other standards, for example, the IEEE, the wireless type standards, they put the sort of average power in the denominator. So there's at least 2 different definitions of EVM floating around. The most popular for optical, because of the IEC, is to use the largest symbol in the denominator. So now when you go to measure the EVM, there's a number of error terms, but most of these error terms can be calibrated out by just measuring those values and then compensating for them in software. So at the end of the day, what's really going to limit your ability to measure error vector magnitude is going to be the sample rate and bandwidth of your scope, and of course the noise floor of that digitizer. So here's just some data that we took on one of our products, just showing how EVM can vary with signal power. So what's happening is when you use a digitizer to look at the output of the coherent receiver, the digitizer has a certain preferred dynamic range. And if you underfill that digitizer, of course you don't want to overfill it, but if you underfill it, you're not going to get all the bits you think you are out of that digitizer. So as the signal gets weaker and weaker, unless you amplify it in some way, you're going to start underfilling that digitizer. So this is an example. The blue curve here is using a 2 gigahertz receiver bandwidth, and the orange curve is using a 33 gigahertz receiver bandwidth. How the received EVM varies with input power. So if you're trying to measure EVM, say, better than 4%, then you would want to use signal powers, above 0 dBm. Now, of course, okay, yes, you could use signal powers down around -20, but the EVM of the instrument is going to start to dominate. So we really recommend that you have at least like a Metro EDFA or some sort of optical amplifier to keep your signal, in the above 0 dBm to get the highest quality measurements. Now, let me just point out one thing here about how this data was obtained. This was obtained using a heterodyne method, where we used a different signal on the signal and on the local oscillator, different lasers. And those lasers then beat together to make a sine wave on the oscilloscope. That sine wave can be interpreted as a phase modulated QPSK pattern. So that's just an example of how you can use heterodyne method, that is two single frequency lasers mixing together in order to test the properties of a receiver. So now shifting gears for a second, talking about measuring the properties of a receiver, these specs, looking back at the OIF documents, are mostly frequency domain specs. They include total harmonic distortion, 3 dB bandwidth, common mode rejection ratio. These are all things that are measured in the frequency domain. And EVM is not one of those because EVM really comes from all of those other measurements. But if you'd like to measure EVM directly, then this is a kind of a nice way to do it, is just to put in a heterodyne signal and then demodulate it as if it was a QPSK signal. Because there's no modulator there, there's not going to be any modulation error, and so the error you measure is from the analyzer itself. Okay, I'm going to move a little bit faster now. I'm not covering as much ground as I had hoped to. I would like to go over some of these application examples. Here's a collaboration we did with the British Telecom, where we used our golden transmitter to put data out onto their link at a industrial park and transmit over to the BT tower and then back again. And then we could look at it with our optical modulation analyzer. And the idea here was to allow them to test different types of modulation techniques and see how their fiber is working. So here's an example of a screenshot of data that we took over their link. And then after analyzing that data, they decided that the wavelength selective switch was actually an important limitation for the whole system, and so then used a filter just to emulate the effect of these wavelength selective switches, and found that the adaptive filter that we provide actually completely compensates for the effect of the presence of the wavelength selective switch, or nearly. There's very small residual penalty from the bandwidth limitation because there's sufficient OSNR to bring that back again through the adaptive filter. So that's one example of how you can use the optical modulation analyzer to look at a system and perhaps see how ready the system is to handle different types of modulation. Here's an example we did at ECOC just last year with 8QAM, and the thing I wanted to point out here is multi-carrier, that this software has the ability to look at one carrier at a time and then present to you the aggregate results. Here we have 150 gigahertz of bandwidth, and you can see the two carriers and the different eye diagrams for the different carriers. This is another example from ECOC showing how the AWG, the arbitrary waveform generator, can be used to pre-distort a signal so that it looks nice after the optical transducer. So here on the left you see the really nice electrical eye, but after going through the E to O converter, it's not so nice anymore. But using the pre-distortion or pre-compensation, now the optical signal looks nice because the electrical signal was pre-compensated. And then here's the same thing for 4-level signals. Of course, you can do it with any type of signal. And then this is what we did at OFC 2015. We actually did a 30 gigabaud dual pole 16QAM signal using 2 carriers. So the aggregate data rate is actually well above 400 gigabit per second. And this was using 4 arbitrary waveform generators. Each one is creating XI, XQ, YI, YQ signals, and then those go to the IQ modulator. That signal is then sent over to the optical modulation analyzer. In this case, composed of 4 70 gigahertz digitizers. These are actually full function oscilloscopes, but They have 200 gigasample per second, 70 gigahertz of analog bandwidth, and we used one of these to look at each of the outputs of the 45 gigahertz receiver. So we had 4 times 200 gigasample per second looking at the output of the Coherent receiver. And then here's the data that we got. And I wanted to point out a couple of things here. One is all the signal metrics. You can't really read them very well in this figure, but we're going to tell you how square the constellation is. That's called the phase angle, quadrature phase, or quadrature phase error. We're going to tell you how well centered the constellation is, if it's shifted up or left, right, if it has any DC bias to it, which is called the IQ offset. We're going to tell you if it's like longer than it is wide, which is IQ gain imbalance. But these are all things you can measure with an optical modulation analyzer. But in addition to this, by applying DSP, you can also learn things about the system. So after we set this up at OFC, we weren't terrifically happy with the EVM we were getting, and so we turned on the adaptive filter. The adaptive filters that are available are very powerful, and this one was able to, here you can see the tap weights. What adaptive filters do is they basically design an FIR filter that corrects for whatever frequency domain impairments are found using some sort of feedback method, either looking at the amplitude of the symbols or looking at the position of the symbols in a, say, a decision feedback loop. But anyways, you end up with a filter, and that filter can tell you something about your system. So in this case, we found this secondary pulse here, but only on the XQ channel, which was indicating a faulty connection over on our transmitter. One of the cables had a bad connector, and that reflection was what was limiting our performance. So just turning on this adaptive filter, not only did it give us the EVM that we wanted, here it's about 5% EVM running error-free, but it also told us the origin of a problem in the system. Okay, so our last section here is on the optical modulation analysis software itself, and I'm running towards the end of the time today, so I'm sorry I can't go into the depth that we might want, but I want to point out a couple things. I think there's a lot of mystery surrounding the optical modulation analysis software. We have different suppliers providing this to the industry. Everyone has their own sort of approach, and I think there's a lot of concern about how do we compare numbers between different systems. Well, I want to point out that a lot of this is actually very common. So, for example, chromatic dispersion compensation. This is basically a textbook FIR filter to remove chromatic dispersion compensation. So this is going to be very, very similar in implementation. The front-end filtering, these are textbook filters. For example, if you're doing a root raised cosine transmit pulse, you would like to apply a root raised cosine filter on the receive side. I mean, this is pretty much a textbook thing. Clock recovery and retiming. Basically, we were most interested in the electric field at the center of the eye slot, and so clock recovery and retiming is necessary. Now this is, and also we need to separate the states of polarization. By the time the signal gets to the receiver, the polarization states have rotated and evolved. So while you might have transmitted your Y polarization vertically when it left the transmitter, by the time it gets over to the receiver, that vertical polarization could be, say, right-hand elliptical. And so the receiver needs to take all the digitized data and figure out what are the states of polarization on the transmit side so they can separate out of those signals. So here's where you can see some variation is how the clock recovery and SOP separation is done. The good news is that for sort of non-pathological signals, that is signals that are really nearly perfect but have some impairments, I think we're getting very similar answers in what I've seen to date between different suppliers. I think there's reasonable agreement on these values. Now, on the other hand, if you have a sort of a pathological signal that has a lot of impairment, I think you're going to see different answers depending on just how well the signal processing being used deals with that particular impairment. So you might need to turn on adaptive filters. As soon as you turn on adaptive filters, now you're complicating things a little bit because this is a real-time filter that's being designed by an algorithm to compensate for all frequency domain impairments that are present. So that will include polarization node dispersion, but it could also and will also include, say, cable loss in the transmitter. So, it's basically fixing everything. So when you turn on these adaptive filters, the constant modulus algorithm is one of them. The symbol-directed or decision-directed least mean square is another example. When you turn these on, it's going to be more difficult to get agreement between the suppliers. I guess what you're doing at this point is perhaps trying to say just how good could the system be if we turn on all these adaptive algorithms. So typically, if you want to compare numbers from supplier to supplier, it's good if you can turn off the adaptive algorithms and just run the open loop or blind algorithms to compare numbers between suppliers. And I think we're getting reasonable results there, and I think things will continue to improve as the industry matures. Now, when it comes to which one do I choose, I think a lot of it comes down to getting the performance that you need, but also just the look and the feel. You know, how does the software feel to use? How easy is it to use? Can I get the results that I'm looking for? And I already touched on this point before. Basically, you can equalize with a blind or a measured value that's corrected, and that's going to give you the sort of the best sort of comparability. Or you can turn on an adaptive filter that can solve all sorts of problems, but it may be difficult to compare that then between different algorithms. And there's a little more data here you can look at later if you want to download the slides and see a little bit more information on configuration settings. But I think what I'd like to do now is move to the last slide so we have time for questions. This last slide here is just talking about if you do have a multi-carrier system, it is nice if your software can handle that to measure one carrier at a time and sort of symbol that for you so you can see the properties of the group of carriers. And so then this is the final slide then, the sort of end-to-end measurement system that we've been talking about today. So thanks a lot for your attention today.
Find out more at Vicom's website.